Hello, everyone. Hello, please grab your seats. There are plenty of seats at the front. My name is Daniela Rus, and I am the director of CSAIL. I want to welcome you to our Dertouzos distinguished lecture tonight. We are honored to welcome Professor Dan Spielman, who's visiting us from Yale. Now, Dan did his Ph.D. at M.I.T. And then he stayed on faculty here for a while, and at some point he decided to move to Yale. So I asked ChatGPT, why did Professor Spielman move to Yale? And ChatGPT said, because he heard that at Yale, the only complexity he'd have to deal with was in his algorithms, not finding a parking spot. So while a student here, Dan worked with Professor Mike Sipser, who is here to give us a more extensive introduction and share some stories about Dan. Mike?
Sure. Thank you. Thanks, Daniela. So why did Dan leave MIT for Yale? Well, he didn't get tenure. No, that's not true. We're not that dumb. Dan moved to Yale, I think, largely because, well, he was an undergraduate at Yale, and I think his wife's family is from New Haven, and Yale's not such a bad place. So anyway, let me tell you a little bit about Dan. Daniela asked me to tell some stories. Dan told me to keep my introduction short. So with that overconstrained problem, I will do the best I can. So Dan is, who is Dan? He is the Sterling Professor of Computer Science at Yale. He's also a Professor of Statistics and Data Science there, and of Mathematics. And he's also the inaugural Director of Yale's Institute for Foundations of Data Science. So Dan wears many hats. He also has many honors. In the interest of time, I'll mention only the major ones, but even that'll take a while. He's got the Fulkerson Prize, a MacArthur Fellowship, the Gödel Prize twice, the Polya Prize, the Nevin Linna Prize, which is now called the Abacus Medal, it's kind of like the Fields Medal for theoretical computer science. He's in the National Academy of Sciences and the American Academy of National Academy of Science and the American Academy of Arts and Sciences, and he recently received the Breakthrough Prize in mathematics. Dan also holds 5 patents. 4 of them are in the area of error-correcting codes. Correct me if I'm wrong on any of this, Dan, please.
It's all right so far.
So far, so good. Okay. But one is in a totally different field. He got it for a device that can tell whether a tennis ball lands in or out. And he got that patent when he was in 11th grade. I don't even know if Dan plays tennis.
My brother plays tennis.
Brother plays tennis, I see. That was to help your brother out. Good. So speaking of breakthroughs, he's got spectacular results in a whole slew of different areas. Error-correcting codes, the simplex algorithm, spectral graph theory, and he solved the Cadison-Singer problem, which had been around for over 50 years, and it had amassed an enormous literature, both in mathematics and in the physics communities. He solved that together with, I believe, your students.
Adam Marcus was a postdoc. Yes. Yeah.
So as Daniela mentioned, Dan was my student, my PhD student. I was incredibly fortunate to have him. I'm glad he chose to work with me. And we were reminiscing this afternoon about how we started working together. And this was very kind of characteristic of working with Dan. At the time, there was this thing in theoretical computer science called probabilistically checkable proofs. And it was very complicated. And so I had some idea for sort of maybe getting a handle on it. I suggested that to Dan. And Dan comes back with a modification of that idea in a totally different field. He used it to come up with a new notion called an expander error-correcting code. And then, it was just, working with Dan was a dream. He was, at the same time, he was very engaged, but also very independent, and kind of did his came up with, built on the things that I would suggest, but came up with a lot of his own ideas, mainly with his own ideas. So I was trying to come up with stories. I asked Dan for some stories. We couldn't come up with much in the way of stories. Sorry, Daniela. So I looked through some of my early emails. I'm a pack rat when it comes to emails. I have my emails going back to the 1980s. And so I found the first email where I referenced Dan Spielman. It was not to Dan. This was back before Dan was a student. It was when he was applying to be a student. So I have it Friday, December 6th, 1991. And I write, "Hi, Shafi and Mauricio. I was contacted by Dan Spielman, who's an undergraduate at Yale, and he's interested in coming to MIT for grad school next year. I don't know him personally, but he already has several published papers in complexity theory, so he's probably pretty good." And at least I got that right. And I also want to mention that Dan is a super nice guy, incredibly modest, and today he's going to tell us about discrepancy theory and randomized controlled trials. So please give Dan a warm welcome.
Okay. Good. Thank you for the generous introduction, Mike. It is very nice to be home at MIT. I want to say I was also very fortunate to have Mike as an advisor, and after we talked today, I remembered actually one of our first conversations back when he was my advisor, and he asked me what I was working on. I told him about some problem, which was sort of a math problem that I'd heard at a computer science conference, and I'd done a bunch of computations and experiments about it, and then Mike asked the most important question. He asked, why was I studying that? And I was like, I heard it at a conference, but I realized I didn't actually have a great justification for studying that problem. So I stopped studying it. And this was, so Mike said I had a lot of ideas. He did give me a lot of feedback. And actually the most important feedback was, is Mike interested in what I am telling him today? If he looked happy, then I knew I was doing something good. If he was wondering, why am I doing this? Time to do something different. And now I have the guinea pig right here in the audience, so we will see how excited Mike is by this. So today I will tell you about sort of two great things that go great together, algorithmic discrepancy theory and randomized controlled trials. I do have one paper on this area. This is the title of it. It just appeared in Journal of the American Statistical Association. It is joint work with Chris Harshaw. Some of you will know because he's a postdoc here right now with Costas and is going to the Columbia Statistics Department next year. Frederick Savvy is a professor of political science at Yale. He's our local expert on randomized controlled trials. And Peng Zhang is now in the computer science department at Rutgers. I'm going to begin by giving you the 1-minute version of my talk, in case you have to leave. The 1-minute version is, back in the 80s, mathematicians did a lot of work in a cool field called discrepancy theory. Roughly what the results in this field tell you is that if you have a set of things, people, vectors, what's the difference, you can divide that set into two sets so that both of those sets are remarkably similar. Okay, we need some way to benchmark remarkably. For now, let me just say more similar than if you had done it at random. But this was sort of a curiosity for a long time. We had no way to compute these. Then there was a revolution around 2010. Nikhil Bansal came up with an algorithm for doing this in polynomial time. And that led to a breakthrough, a whole lot of other algorithms for solving problems in discrepancy theory. So now we know we can find these divisions into similar sets. The question is what to do with it. I mean, theorists love it, but what to do? So I maintain a great application for this. There might be others, but I see the great applications for designing randomized controlled trials, where when you want to test something out, you want to give some people a placebo and some people maybe a medication or something like that. You want to divide them into a test and control group. You want those groups to look similar. Discrepancy theory gives you a way to do that. But we need more than just discrepancy theory because we have to have some randomness. So we sort of need a random version of discrepancy theory. And the summary is what you get out of this is you get better estimates of the effectiveness of the treatment you are trying without risking doing anything bad, which is my first rule. Do no harm by giving people algorithms. So it's not going to make things worse. So we can limit how much worse it could ever be. Okay, that's the 1-minute version. Now let's learn about discrepancy theory. So the problem that really excited me in discrepancy theory that I first saw is one studied by Joel Spencer. So imagine I have a bunch of people. I've called them P1 through P8 here. Imagine I survey people in this audience, and then I write down some information about them. I learned statisticians call these covariates. I write down, are they a mathematician? I'll put a 1 in the column if they are. Are they a computer scientist? A 1 in a column. Some people here are both. I can mark a 1 if they're a student, and then we can write down what editors they use for LaTeX. And now imagine I want to divide these people into 2 groups that are similar. Like imagine we're doing trivia night at CSAIL, and we have to make 2 teams, and darn, those Emacs questions are hard, so you got to have a deep roster on both of them. Okay, so I want to divide these into 2 groups, and now the way I'm going to measure similar is I'll take a look at how many people say are a member of each group. Sorry, like how many people in group, I'm going to divide them into group A and B. Let's say I have this added a column there, I hope you can see in purple. I assign some people to group A and group B. And I want the sums of the vectors for each person to be similar in each group. So the way we'll test that is I will write down the sum of first for group A. The first row there is you see the 2 there is the number of people who are mathematicians in group A. I'll write the sum for group B. And we'll look at the difference of these 2 vectors. And we're going to look at the largest magnitude of an entry in the difference. In this case, there's a -2 there. So that is the largest magnitude. The biggest difference between group A and group B is how many people are students. So this is a sort of discrepancy problem you can study. People try to make these groups as similar as possible, at least in these sums. So what Spencer did is Joel Spencer compared look at what happens if we divide the groups at random. That's the first instinct of a computer scientist. Given a tough problem, try a random solution. How do we do it random versus what can we actually do if we're really thinking about it? So if I have n people and d covariates, and you assign them at random, you expect basically some entry of the difference to be around root n log d. And Spencer proved that if you do this right, at least when n is more than d, there are other results for the other direction, but let's think about n being more than d, you can make sure, by the way, I'm going to call this difference diff. So that's the difference vector, and we talk about the largest absolute value of an entry, that's the infinity norm of it. So this is how I'll write the max difference. By the way, I've also I tried to keep formulas low in this talk. If there are questions, please ask. We have a board. I didn't know I was going to have a board, so we can use it. Okay, Spencer proved you can get this difference, all these entries, to be at most 6 root d. So there are 2 things that are remarkable here that say this is better than random. One, d is probably much less than n. Okay, if we think of d as being less than n, then this root d is much better than that root n. But actually, Spencer didn't focus on that. Spencer, the beginning of his paper deals with a case where n is equal to d. It's a natural diagonal case. We got 2 variables that start by making them the same. But even then, this is considered exciting, because even when n is equal to d, in the random case, you lose this root log term. And Spencer had 6. And the root log grows with n or d, and the 6 doesn't. And that is one way of saying it's much better than random. Okay, there's one caveat for that. If you're used to looking at numbers, you know that root log n is usually less than 6. Okay, but 6 is also not 6. So even in Spencer's paper, that 6 was a 5.3. He just called the paper, he wrote down 6 because he titled the paper 6 standard deviations suffice. Sounds better than 5.3 standard deviations suffice. And then if n is small, you can actually get better bounds than 6. So really the message to take away is you can divide these groups much better than you could at random. And please come back. Thank you. Okay, I want to mention one other discrepancy problem. By the way, should also add Spencer's problem. It's an existence proof. There was no algorithm. People wondered for a very long time if there was an algorithm. People conjectured there was no polynomial time algorithm because we had no idea how you would make an algorithm that would do this. and all of the basic attempts failed. And Spencer tried to give some argument about why it was hard. Okay, here's one that we actually could do effectively, where there was also a difference between n and d. It's considering Euclidean norms of vectors. So imagine I give you a bunch of vectors, n vectors in d dimensions, and let's say they're unit vectors, or norm at most 1. And now I want to assign some signs to them to add up the vectors. So the sign should be z of I, that's the sign I'll give to vector I. It's a plus minus 1, and I'll let s be the signed sum. So sum every vector with its sign. And let's see what happens if we pick random signs. So actually, I should have been precise here. If I write random signs, the expected Euclidean norm of the square is n. Exactly, in random signs. But OK, since I didn't square the Euclidean norm, let's just say the expected norm of a signed sum with random signs is around root n. Combining works of Baran and Grinberg and Beck and Fiala, published in '81, you can get an algorithm that picks signs that gets a 2 norm of the signed sum being at most root d. No constant, sharp, root d. And this is tight. You can't do better. If you want to see why, just imagine I give you d elementary unit vectors. Whatever signs you put in front of them and sum them together, you're going to get Euclidean norm root d. Make the other vector 0 if you like. And it comes with an algorithm. OK, this is not sort of as strong as Spencer's theorem. It's not obvious, but if you convert between the norms, neither one implies the other. But it's maybe slightly less impressive, but it had an algorithm, and it's a good case where n differs from d. I do want to mention this algorithm was essentially rediscovered by Deville and Thiel, who invented something called the cube method for survey sampling. They were interested in doing like government surveys. They were working in France, where they have all of these villages, and they don't want to survey every single village every year. So they just wanted to pick some small subset of them to survey every year. And they didn't know about the work of Beck and Fiala, but they basically reinvented their algorithm and do something very similar, except they throw some integer programming in at the end. And so they were less involved in the theorems, more involved in, hey, integer programming does a really good job at this, after they throw some algorithms. So there's one connection between this work and the sort of statistics literature. This has since I know been used in many, many places. There's a big literature behind it, though I mainly know it being used in Spain a lot. OK, but you could be asking me, yeah, should I say 2 sets are similar if their sums are similar? Like, I mean, that's something. But if you take a look at like my people in trivia night, it could have been like one group could be students who know Emacs and professors who know VI, and the other group could be flipped around or something like that. Like, we're talking different demographics. So like here I give an example. Here are 8 vectors, and I've divided them into 2 groups. Hopefully I hit anyone who's colorblind or anything like that. Some are purple, some are shaded. And the sums of these groups is just at the center. This is the sum of both groups. So the sums of these groups are the same. But I would say that this division of these vectors into 2 groups, those 2 groups don't look similar. And you can see this because, like, one group is basically on one diagonal and another group is basically on the other diagonal. And if we want to make that a little bit more formal, I could say, let's take a look at the moment ellipses of the group. Before we were looking at the sums, it's like a first moment. Now we can look at moment ellipses. And the moment ellipses of one group is diagonally this way, and for the other it's diagonally that way. So they're very different. But as you can see, it's possible to divide them into 2 groups where the moment ellipses are more similar. This is sort of getting at a higher order information than sums. And actually, you can prove that this can always be done. So this was Weaver's conjecture, which is what Mike mentioned that Nikhil Srivastava and Adam Marcus and I resolved when we solved the Cadison-Singer problem. We proved that you can always divide these vectors into 2 groups so that the moment ellipses are similar. I'm embarrassed to say we still don't know if you can combine this with a previous result. We don't know if you can get the moment and the ellipses similar and the sum similar. And we don't have any algorithm for this. We're pretty far from algorithms for this, except in very low dimensions. But this is another sort of notion of discrepancy you can push that gets you to more similarity. There was a lot of work, especially in the 80s and 90s, on discrepancy in low dimensions. And there they were able to get much stronger notions of similarity, which I deleted from my talk, but if there are questions at the end, I can show you. So I'm saying, like, in especially 2 dimensions, 3 dimensions, you can really divide points into sets that are very, very similar. I reference Bernard Chazelle's book for a lot of work in this area. But there were interesting things going on. There are connections to VC dimension, and one of the main concepts from machine learning. This was used to de-randomize algorithms. It was used to construct lower bounds. So there was a lot of work in low dimensions, and a lot of this was very, very algorithmic. But the high-dimensional things like Spencer, people still had no idea for a long time. Until this breakthrough of Bonsall that I mentioned earlier. So Bonsall came up with an algorithm for solving Spencer's problem in polynomial time. Now, it wasn't 6 in front of the root d, unfortunately. It's a much larger constant. I hope you'll bear with us, theorists. Once we know that something is a constant, we proclaim victory. But unfortunately, other people work on getting it down, and we got the constant lower and lower. And people, after Bonsall's algorithm, it really sort of showed a new way to design an algorithm for something. And that's part of what excites me about algorithms. Like, I get very excited whenever I see a new algorithm, even for a problem I know how to solve. If it works fundamentally differently, that's cool to me. But here was a problem that just no previous algorithmic paradigm solved. So it forced someone to think of something different. Actually, I'll show you a little bit about how algorithms for this work. OK, so what happened after Bonsall was people came up with other algorithms, solved a lot of other discrepancy problems. A lot of them we can solve algorithmically now. Unfortunately, not that moment ellipse thing yet. I'm still hoping someone figures that out. And a big question for me is, what is the right constant that we should have for Spencer's theorem? He stated 6 at the title of his paper. We knew 5. I've seen proofs circulated that get something around 4. I'm conjecturing the best constant is 2. I will be really happy if someone can either prove or disprove that. But I don't know any reason it shouldn't be 2, which would be a very strong result. OK, because I get so excited about seeing new algorithms, and I hope that some of you do too, I want to at least tell you a little bit about a way of making Bonsall's algorithm work. It's not exactly Bonsall's original algorithm, but it's an improvement of it, a simplification. So I should first tell you the idea of Spencer's proof. Spencer's proof had an outline which was semi-algorithmic. He said, OK, I want to find some vector z with all entries that are plus minus 1. And then I wrote S of z for the signed sum of my vectors. So S is the sum depending on z, and we want that to have low infinity norm. So instead of going for plus minus 1 initially, let's try to find something that's got entries that are plus 1, minus 1, or 0 that has low discrepancy, but where at least a lot of the entries are plus minus 1, like at least a third of them. That's what Spencer did first. And then he said, OK, if we can do that, then we're going to start fixing up the 0 entries. He proved that if you can accomplish that first goal of getting a lot of plus minus 1 entries and a bunch of zeros, then you can work recursively. But there wasn't an algorithm to come up with that thing that would get us most of the entries in plus or minus 1. That's what Bonsall figured out. And I will tell you just roughly Lovett and Mecca's algorithm. It's a refinement of Bonsall that's very, very clean. And you can find blog posts about it. Like there's one by Salil Shram that's really nice. So here's how their algorithm worked. First, we're going to do something that's not crazy. We're going to make the problem a continuous one. So instead of looking for vectors that are plus minus 1 entries, we'll look for vectors that are with real number entries between 1 and minus 1. And you take a look, and if you take a look at all the vectors with real number entries between 1 and minus 1, that's a polytope. It's the hypercube. And then we take a look at another polytope, which is sort of our constraint. If you say, for which vectors, when I sum up, when I take these signed sums, so now they're not signs, now they're real numbers. For which z's, does that have bounded infinity norm? That's also a polytope. It just looks a little different. So we want those to have norm at most root n. And we're going to take a look at the intersection of those polytopes. And their goal was to find a point that's in the intersection of these 2 polytopes where most of the coordinates were 1 or minus 1. And they do it by Brownian motion. Okay, I gotta admit, when I was a graduate student here in applied math and theory of computing, I thought I would never have to learn differential equations. That was the other end of applied math. Turns out I was wrong. So now theory of computing students have to learn stochastic differential equations, and I have to try to keep up. Okay, so what do? We start from the middle, And we keep walking, and when we hit a face, we'll just stay on that face of the polytope. Here, I drew a better picture for 3D. Let me give you the better picture. So this is the ordinary hypercube. Then I take a look at this constraint. I'll intersect it with all of the vectors that don't lead to big discrepancy. It basically slices off a few corners. You can show that that condition, not getting bad discrepancy, leads to a polytope that's much bigger. So really, it's sort of the right picture. It's not slicing off much of the body. And then you start in the middle and do Brownian motion until you just sort of randomly walk until you reach a face. And then when you hit that face, you say, I'm going to stay there. And now you only walk within that face. Okay, that challenged my artistic skills a little more, but imagine that was only walking in that green face. And eventually it's going to hit a lower dimensional face, in this case an edge. And then you can walk in that edge. So you probably walk up and down a little bit until you hit a corner. And okay, yeah, here it finally hit that corner. And then you can prove, it's not too difficult, that most of the coordinates of that corner will be plus or minus 1 in this case. That is just a totally different way of designing an algorithm that I'd ever seen before. Okay, I say, there are a few other reasons theoretical computer scientists need to learn about Brownian motion and stochastic differential equations. One, because, not just this algorithm. There's work of Ron and Eldon, work in convex geometry. And, oh yeah, diffusion models are a really good one, where now everyone has to learn stochastic geometry. Yeah, Charles. Yeah, the very last step, but only one-dimensional step. But yeah. Yeah, when you're in one dimension, you can get rid of that.
No other plan for higher dimensions, I gather.
No, okay, there are de-randomizations of this, but really, they don't give me more insight. I like the randomization. But there's a good question. Now that we know you can do this, how else can you do it? There are all sorts of heuristics out there you could try. And I did, because I actually want to make this technology available to people. I'm sure that there are many people out there who want to solve discrepancy problems. I've talked to high school teachers in my town who, over the summer, they spend time trying to divide up this couple hundred incoming kids into classes, and they want each class to look the same. And some poor soul is spending weeks with a spreadsheet, moving students around, and then discovering, oh no, this class is all the baseball players. So I want to make this solvable.
A lot of bias.
Yeah. So what do you do? Well, okay, we've tried, and my group and my student undergrads mainly, have tried a lot of algorithms. What we discover is pure naive heuristics don't get you very far. You get okay solutions, but you can get much better if you incorporate a little bit of knowledge from the algorithms that have been developed and then throw in some heuristics to make it a little better. So you need some of the algorithms. And okay, so now one of my students, oops, is this coming up? Please come back. Daeyeon Lee has an app. You upload it a spreadsheet, and it gives you back a CSV with an extra column. And all the compute is done in your browser, and which is why you tell it also, I don't know if you can see, how many minutes you want it to run for. The more minutes you give, the more heuristics it will try, and it'll let some of them run for longer. We're still optimizing this. But at least and by the way, you don't have to memorize the URL. I have a link to it on my webpage under my software section. So people can at least start playing with this. Actually, I also hope that this is just a challenge for other people to design better heuristics and code that does a better job on average. Because especially if you want it to run on the user's browser, the Brownian motion-based algorithms are a little intense to implement and don't get the best constants. Okay, that's all I'm going to say about algorithmic discrepancy theory for now. I want to tell you about how I got into randomized controlled trials. Maybe I should pause for questions if there are some about discrepancy. Pablo, yeah.
If you do the linear programming relaxation and bunch and bound, how well does it work?
Oh, that's a really good question. So, by the way, first, linear programming relaxations, there's a paper of Rothfuss that gets actually some decent heuristic based on linear programming relaxations. The branch and bound, okay, I did try this at some point, or I am not sophisticated about branch and bound. I used off-the-shelf, like Cplex. It didn't give me great answers. It was not as good as the heuristics we implemented. Your mileage may vary, but yeah, that was one of the first things we tried. at some point. Yeah. Oh, sorry. I forgot to repeat the question. The question was what happens if we do integer programming in branch and bound? And I was going to say, yeah, like Cplex did not give great answers to this problem. In higher dimensions, if you're like 20, 30 covariates, but there you can also just brute force search it. Oh, yes.
Brownian motion, could you just randomly pick a face?
Because, well, okay, it's a good question. The question was, why do you need Brownian, why do you need Brownian motion? Why can't you just pick a face? Well, okay, so you can identify the faces of a polytope. It takes a little while, but you need a measure on them. You don't want to pick one uniformly. And this seems to give the right measure on them. And then recursively, as it goes, it keeps using the right measure. But actually, the proof that you get this way is remarkably simple. So that's also a nice feature. And it's got something to do with Brownian motion. You keep track of time. Yeah, Charles.
Into 3 approximately equal sets.
The question was, what if you want to divide into 3 approximately equal sets? 3, okay, so there are ways to skew the size of your sets. So like we could make one to be 2/3, one 1/3, and then split the other one in half. As far as I can tell, that's about the right thing to do. But this is a good segue, because the question I was asked was about splitting into 16 sets. So here's what happened. My colleague Nicholas Christakis, he and I used to run an institute together, came to my office one day. He was setting up, he is a professor in sociology and public health, and he was running a public health intervention. They were trying to test interventions to improve maternal health outcomes, and they were testing this in villages in Honduras. This was a very big study. They had 176 villages they were doing a study on. Each village was getting a different intervention. They were village-wide interventions. They had 16 different treatments they were trying. So 16 interventions they're trying, which means they needed to divide these villages up into 16 groups of 11 each. And here I've sort of plotted these villages by latitude and longitude and assigned them a color based on which group they get in a random assignment. So Nicholas came to me because he was not happy with the results of random assignment. Okay, to be honest, he was doing something a little better than random, but let's not discuss what. Let's think about random for now. And the sort of problem he's finding is it might be that all of the villages in one group, say, could wind up on the western end of the region. That's those red ones here, and those are all the red points from the left figure that I generated at random. Why could this happen? It's the law of small numbers. When you take a few random samples of things, you tend to see patterns. Flip a coin 10 times, there's a good chance it comes up the same 4 times in a row. You think that's a biased coin or a pattern, but no, that's just law of small numbers. And then, of course, he wasn't just worried about this happening. He says, if this happens, he won't know if that group does particularly well. Is it because of the intervention they got or something going on that side of the country? I mean, even worse than him not being sure of that, a reviewer could question that. Another one, and by the way, this was me generating random examples. A bunch of villages could be in a middle latitude. So, this doesn't seem good. He wanted something better than the random assignment. And more than that, I say this is a big study. They knew these villages in great detail. They had measured many things about these villages. They knew about the altitude, distance to hospital, median income, all sorts of socioeconomic measures. They had about 25 covariates, and they wanted all of those to be similar in every single group. He said, can I help them? I said, yeah, sure. I mean, I know algorithmic discrepancy theory. I got you. And I even have code for a lot of this stuff from my work on the Cadison-Singer problem. I did make one request, though. I did request that he prioritize these covariates. Because, there were a lot of them, and some seemed like they were unlikely to be important, and maybe we shouldn't weight them as much and weight some others more. Okay, given that, I came back to him with an incredibly balanced assignment. We ran code for, a couple hours, and it came up with something like this. Okay, you can't quite see from the picture, but each of the groups is balanced very nicely geographically and according to all of the measures we had. And then Nicholas was not happy. He said, how does he know that this is not going to somehow be worse than his random assignment? And I'll admit, like, my first reaction was like, what bad experience did you have with an algorithm? Like, why do you think my algorithm would somehow be worse? I was offended, but I got over it. I realized he had a legitimate concern because you need randomization. I mean, I could say, I don't think it could be worse. I don't know how it could be worse, but that's not a rigorous mathematical statement. That's not statistics. In order to actually argue the observed results of your study run like they do to chance, you need something random. There has to have been some chance somewhere. And a great place to get that is through your assignment of subjects to groups. If you want to make confidence intervals or p-values or any of those things that appear in all of the publications in public health, you need something random. You need randomization. But not just that, randomization helps. And I will show you pictorially why in a moment. But you do things at random, you can balance things better at random, sort of on average, than you can in the worst case with any particular assignment. So what I learned was that what he wanted to solve was not really exactly an optimization problem. He did not want one particular assignment of low discrepancy. Maybe he wanted the best distribution on assignments of low discrepancy. But what he really needed was a distribution on them. So I said, okay, like here are 100 of them. They're all very different. Please pick one at random. And that's about as good as we could do because he asked me this a month before the study was due to begin. So, sorry, that's only 64, but I can't fit 100. But they were, all low discrepancy, all very different. Okay, so that's how I got into this problem, and that gives you some of the motivation. Now I can give you a way of making this rigorous and understanding and formalizing the concerns that Nicholas had. So I'd like to do that. And for this, I will appeal to the Nyman-Rubin potential outcomes model. It's a very powerful model for analyzing experiments. Let's stick with having two groups. Let's not think about 16 right now. Though addressing Charles's question, again, dividing by a tree is pretty darn good. I don't know if there's anything better yet. That problem bugs me. Okay, let's say I have two treatment groups. We'll call them a test group and a control group. In the potential outcomes model, we say there are two potential outcomes for every subject of your study. A subject could be a village, could be a person, could be a school in which you're testing something. The potential outcome for subject I will be A of I. That's what you observe if subject I winds up in group A. You observe little b of I if subject I winds up in group B. Here's the key point. You never get to observe both potential outcomes. Like you either gave them test or you gave them control or you gave them one intervention or you gave them another. If you learn A of I, you can't learn B of I, and vice versa. So that is the challenge in this business. And we are going to assume for now that the only randomness is the choice of assignment of subjects to groups. So I'm not going to assume that A of I or B of I are random. If you want to, you can, but just imagine you sample and fix that randomness in advance. It won't really hurt too much, unless you're a Bayesian, in which case you're probably very annoyed at me now. But let's not worry about that. Any Bayesians here? Nothing has been thrown so far? Okay. But an old friend who's a Bayesian, so I'm safe. Okay. Okay. So we'll just assume that the assignment to treatment is the only source of randomness. Now, when I talk about a design, an experimental design, we mean the distribution on assignments of treatments to control or test. So how do we choose these groups? So I think the most obvious natural design is just uniform. Flip a coin for each subject. Comes up heads, they go in group A, tails, they go in group B. Sometimes you think you want your groups to have the same size. If you do, well, another thing I'll say, uniform balanced. Just let A be a random subset of half of the subjects, B can be the others. Another one people study a lot is what are called matching designs. Here you take your subjects and you put them into pairs that are similar to each other. So if two subjects are similar to each other, we'll make them a pair, and then for each pair, we independently flip a coin. If it comes up heads, one is in group A, while the other's in group B. If it comes up tails, you flip it around. That's called a matching design. It's a common thing to do. Those are three good reference designs to have in mind for now. I'll give you another, but this is where we'll start. So another question is, what do we want to measure? One of the main things we like to measure is average treatment effect. That is the average of what happens to the subjects if they're in group A versus group B. And we'll call that tau. So this is often when you figure out, this tells you, like, how much better is group A than group B, if being positive is good. We're going to estimate it by one of the most naive estimators possible. It's called the Horvitz-Thompson estimator. It just is, okay, we don't need the fancy name here, sum over the little a of i's for all the i's in group A, sum the little b of i's for the i's in group B, and subtract them. So this is like the most naive thing you can do. I observe some things in group A, I observe some things in group B, I subtract one from the other, put in the right normalizing constant in front, which is 2 over n, and this is our estimator tau hat. Oh, by the way, one thing to know if you're not used to statisticians, when something is an estimator, they put a hat over it. So like right now I'm Dan, now I'm an estimate of Dan, okay? Now you'll remember. Okay, so tau hat is our estimator of tau. You do this right, in expectation tau is correct. So that means tau hat is right. So the expectation of tau hat is tau, so that's good. But we really want to worry about the error. So what is the error? Well, we can actually write down a formula for the error, which you don't need to know particularly, you just need to know it's an inner product. What you do is it's the inner product of z, that's my vector of signs, so it's plus minus 1s for the subjects, telling you, oh, like it'll be 1 for the subjects in group A, minus 1 for them in group B. So it tells you who goes where. You take the inner product of that with A plus B. I know this is a little counterintuitive. So A was one vector of potential outcomes, B was the other vector of potential outcomes. You add them together. We get a vector I'm going to call mu that we use a lot. So it's the inner product of z with mu. And this is true for any design. So you give me any design, this is the error of the Horvitz-Thompson estimator. The reason I want to point out its inner product is, in a moment I'll point out why it's an inner product. First I want to address a question I always get. Why not use something fancier? I mean, like, you go to a statistics class, you learn about linear regression, you learn about logistic regression, you learn about all these other things. And, there's machine learning things you could do. So why not do something fancier? I'm nervous about doing things that are fancier for 2 reasons. One, even the plainest linear regressions, when you have noise in your data, that noise can drive your estimator. And if you do a lot of experiments, sometimes that makes your estimates worse. And it can make your estimates of treatment effects worse in unreasonable ways. Like, if I'm just subtracting one bunch of numbers from another, that can't go too far wrong. You start doing some regression, it can go pretty far wrong. Now, it's not completely fair. There are places you can understand this, but mainly I just want to say it's not well understood in general what happens when you apply corrections based on regression. Unless, like, your number of subjects goes to infinity. If your number of subjects goes to infinity, then you can talk about what regression does, and you get very clean formulas for it. But our number of subjects doesn't go to infinity. Like, doing a study on 176 villages in Honduras cost about $10 million. So, we don't want to do an infinite number of villages. Also, if you let n go to infinity, I will tell you that if you use the designs I'm going to explain to you, you get the same results using this plain Horvitz-Thompson estimator, which can't go too far wrong. But I'll explain that in a bit. I should mention, though, there's like one exception to this. So, there's this recent paper. I don't know if Jaridi is here. I know he's a postdoc somewhere at MIT. If he is, please wave. Oh, hi. OK, cool. Right, so they have some analysis now for what happens when you do linear regression that can apply before n goes to infinity. But it is still not tight, but hey, it's a damn good first step. And OK, maybe they have a second step as well. So I'll mention the paper. OK, back to just the Horvitz-Thompson estimator. So I told you that your error is the inner product of this sign vector. Well, there's one in n, but this z vector is with mu. Oh, here I wrote it as z transpose mu, but same inner product. Sorry, I changed notation. Here's the thing to note. If you look at that, z could be near mu. But if z is like a random plus minus 1 vector, if you pick a random plus minus 1 vector, it is very unlikely to have large inner product with any target vector you had in mind. In particular, if like in high dimensions, and here the dimension is the number of subjects, a random plus minus 1 vector is usually almost orthogonal to any vector you want with pretty high probability. So you can be pretty sure that the angle between z and mu is about pi over 2, 90 degrees minus 1 over root n. That happens with pretty high probability. Actually, once n is about 10. So, random is pretty good. And this is some geometric intuition for why you might want a random design, but we can do better. OK, so to talk about how you can do better, let's take a look at a first measure of error, mean squared error of an estimator. We also reason about tails. Let's save that for later. But if I have time, I may skip it. Mean squared error, that's just like, what is the average squared error of our estimator? And if we look at a uniform random design, which should be our baseline, we get a mean squared error of 1 in n squared times the squared Euclidean norm of mu. And here's what's somewhat disappointing. That's as good as you can do. So if you say you want to do something other than just flipping independent coins for each subject, your worst case is going to be at least this bad, usually strictly worse, unless your choices are pairwise independent, which they're probably not going to be. So from a worst case perspective, the best design is just independent coin flips. But you can imagine there could be things better. How can things be better? Because maybe you have some covariates that are predictive. And if they are predictive, then you can get lower mean squared error. And you just want to know how much can you mess things up. I mean, let's even look at a simpler case. A lot of us have an intuition that our test group and control group should be the same size. So how do we justify that from this perspective? If I pick a random z where half the entries are going to be 1 and half are going to be -1, the mean squared error I get looks like this. The first term is bigger. Before I had a 1 in n squared, here I have a 1 over n times n minus 1. So that's worse. But the next term is better. With the IID design, the term I had there was the Euclidean norm of mu squared. Here, we are taking really what you get by taking mu and subtracting off the mean from every entry. That's what this is. This is the square norm of mu minus the mean of every entry. And if mu does not have mean approximately 0, that was the sum of my potential outcomes, this will have a much smaller norm. So, and when does it happen? Well, imagine a lot of studies that say, I don't know, how many years does someone live after you give them a treatment or the control? Those are all positive numbers. So in that case, A and B is going to be positive, mu is going to be positive, mean probably won't be near 0. Then you can imagine this will help improve things. OK, so this is at least a formal way to see that sometimes if you have some guess about your data, you can pick a design that does something better. And that's making half the entries in group A and half in group B. I will add, I'm sure some of you are thinking, but maybe I can estimate the mean and then use that to correct. And I will just tell you, yes, you could, but you could just use this design. And then you're not doing anything to torture your data. You're getting this subtracting off the mean for free. We don't compute that. That's just an artifact of having made half the entries in group A and half in group B. OK, so what we do in our paper is we define two properties of a design. The first we call robustness. Formally, it's the largest eigenvalue of the covariance matrix of Z. It corresponds to our worst case error. It's always at least 1. It's 1 for the IID design. Let's say it measures the worst case. The other thing is balance. That measures how well our design balances the covariates. Formally, it's the largest eigenvalue of the covariance matrix of the signed sum. You don't need to know those formulas, but if you like them, now you know them. This measures sometimes the worst case error. If our potential outcomes are actually just like linear functions of our covariates, that would be the dream case. Then this measures our worst case error. But more importantly, this also upper bounds the mean squared error of our design. You give me any design, we can plug in balance and robustness and get an upper bound on the mean squared error. So that's like how much error we should expect. It has this expression that looks like what's called a ridge regression. So there's a minimum over beta. Those are like measuring linear functions of the covariates of the norm of a linear fit of our outcomes on the covariates plus something which is the norm of those coefficients. And the balance and robustness term up here, there's some cross terms that don't matter. So any design we can upper bound this way. So now we have sort of a framework that gives us a rough idea. We can measure these things of a design and figure out how good it is. And what we introduce is what we call the Gram-Schmidt-Walk design, which trades these off very cleanly. You pick a parameter phi. That's the trade-off you want. And we can guarantee that your robustness will be at most 1 over phi, and your balance will be at most 1 over 1 minus phi. I've got some scaling here. My vectors should be at most unit vectors. So we can trade these off. And then actually, if you look at our mean squared error, we don't even have the cross terms. So this says that the mean squared error of the design looks like this ridge regression, where I can put in a 1 over phi here and a 1 over 1 minus phi here. And this is like what you would hope to get in the infinite sample limit if you were regressing all of those potential outcomes that you don't even know what they are. But it happens just because of the design we choose, which is this Gram-Schmidt walk. All I want to mention in this slide is that the sort of right choice of phi, if n gets pretty big, it doesn't have to go to infinity, 10 times d or something like that, phi should grow to 1. So you actually want to choose phi so that your design is incredibly robust. That means it can never be much worse than IID, but it can be much better. And in the paper we work out, under different regimes, what is the right choice of this phi. But usually you're going to want it to be near 1. So that's why I say you can get much better estimates of treatment effects if you're willing to risk being a teeny bit worse in the worst case. You might ask, how does a matching design do? Well, the robustness is always 2. You can see it if you look at the covariance matrix. But it turns out that the balance grows with n in any dimension larger than 2. So if you have 2 covariates, you're fine. But if you have like many, even 3, and you let's say random points, your balance term gets bad. Why? Just because the more data you have about things, the less likely you are to have good matches. Oh, and then there's some annoying parity conditions that you get on matches as well. But I say people seem similar until you know them better, and then you realize they're different. The more covariates you have, it changes. Okay, the Gram-Schmidt walk came from this amazing paper called The Gram-Schmidt Walk, A Cure for the Banachik Blues by Bansal, Dadouche, Garg, and Lovett. I will just tell you, because I want to finish in 3 minutes, roughly what their paper does, and then work to a conclusion. So they were coming up with a polynomial time algorithm for discrepancy problem. The discrepancy problem is not randomized. It's called Banachik's problem, but they got there by a randomized algorithm. And what the randomized algorithm does is it takes a bunch of vectors as input, x1 through xn, assigns them signs, and they prove that this thing gets balanced at most 40, or that the signed sum is at most root 40 sub-Gaussian. And that gave them an algorithm for Banachik's problem. So they generated this random sampler. Most of our work of our paper, at least the first version, was all done getting that constant 40 down to 1. So it turned out their algorithm was the right thing to do. We just had to reanalyze it. And 1 is the right constant for it. Why did I have to do this? Because this number factors into the width of confidence intervals that you produce in the end. And if I tell experimentalists that, hey, this confidence interval won't be a factor more than 40 larger than necessary, they will just kick me out of their offices. So 1 was the right number. Let me skip all of this. I'll skip telling you how the walk works. Let me just tell you about a few related things in the open problems I care about. Actually, here's the key open problem, the online version. So I was talking about, I started working on studies where you know all your subjects in advance. Most medical trials don't work that way. Most medical trials, someone walks into your office and you got to decide, do they get the placebo or do they get the vaccine or something like that on the spot? Okay. You can ask, what do we know about discrepancy theory in this case? Well, there's some pretty cool results. First one here from MIT, San Swanee from MIT, Lou from Stanford. If you look at their paper, they have a paper on online discrepancy. It gets something that's root 2 sub-Gaussian if you're willing to ignore the results from about 5% of your subjects. Okay, the biostatisticians I talked to are completely happy to ignore 5% of their subjects. They're not happy about root 2 as opposed to 1. But, oh well. Improvement, maybe of Kulkarni, Rees, and Rothfuss. They get something root 10 sub-Gaussian. By the way, the first one, that's got like a really good algorithm. It's very simple. The next one is a doubly exponential time algorithm, but you don't have to ignore some subjects. So that may be progress. But I conjecture, and I'm completely convinced, that we can do online with the right balance 1 sub-Gaussian. And that should be possible. Okay, to stop, let me finish with just one statement. Again, many people ask, should we use some machine learning or some sort of regression? All I want to point out is you use this design, and that mean squared errors you get, and the tails of them agree with what you would get if you did a ridge regression of your covariates on actually the sum of the potential outcomes. So it is baked in, it's an artifact of the design, and you can use a simple estimator. And I like this because in the next few years, people are going to be using AI to suggest all sorts of interventions and treatments and ways we can improve society. And they will be suggesting this based on the AI. They might not have the same sort of level of intuition that people do now. I mean, when people are designing drugs now, they understand a lot about the biology and physics and chemistry going on. They might be saying, the computer gave me this. Okay, so we need to get really good at testing what really works. And actually, for me, sort of the nightmare is that not only do we have something from an AI proposing the treatment, but we have some AI algorithm deciding that it works. That would be a little too divorced from reality for me. So I think that this is a subject where we need a lot of work and a lot of better mathematics and statistics and algorithms. And there's a lot of opportunities in the area. So I hope some of you will join me and others in working on this. Thank you.
How important is it for the medical profession to understand the data science aspect?
Oh, okay. So the question is, how important do I think it is for the medical science people to understand the data science? And the answer is, ideally, someone should understand both. I mean, but we also have to be realistic. There are a few MD PhDs out there who can understand both. I think the medical practitioners need to talk to biostatisticians who then understand the data science and the work. But they work in big teams. And I would love if my doctors or the people actually doing medical studies all understood the statistics or the data science of it. But I do feel that that's unrealistic, except for very few rare cases. Just because, you can only learn so much in 2 or 3 graduate school careers. And that's like what our doctors are doing.
Other questions? There are microphones. It's your chance to ask a deep data question to our distinguished speaker.
Great presentation. I want to go back to Fisher's original framework, which was that randomization was supposed to balance both known and unknown factors. And I'm wondering if you're paying a price here with the balancing of the unknown factors and where that leaves you.
Right. And this is always something you worry about. There are these unknown factors that in this case, you can understand them by taking a look at the robustness term. So if there are unknown factors, I can't balance them. But the robustness term that appears in our analysis says that we can't have done anything too bad with them. So we're handling them pretty well. And that's part of why we needed random assignments here and a lot of randomization. It's a good question.
Well, while you all are thinking about new questions, there are microphones. Please come down. I have another question for you, if I may. So I was struck by your statement that you prefer to use this simple measure instead of more complex measures like regression because there's uncertainty in the data using complex measures.
Let me clarify. If your data is not nice, so I did say noisy, but it doesn't even have to be noisy. If you take a look, I've just done this example many times of taking, just sort of simulating this on the computer. I mean, there's a problem, I should tell everyone. This is the big warning in this area. There are no good benchmarks. Because if you take a look at studies, we never observe both potential outcomes. So that's a bit of a problem. Unlike a lot of the machine learning world, where we can test our algorithms against benchmark data, We do not have studies where we know both A of I and B of I. We do not have studies where we know, like, how well people would have done if they didn't get the COVID vaccine, but you gave them the vaccine, so now we can't know. So we don't have great benchmark data, so what can you do? You can try to do simulations. And at least in some simulations that I've done, doing linear regression actually makes your errors much worse. So it can be bad. And now, of course, there's randomness in my simulation, and it depends a lot on how you set up the simulations. And people can debate a lot about how you would set them up. But for me, the main concern is I don't have a great mathematical understanding of it. Like if we take your paper and turn that 8 into a 1, then I might say, yes, let's do linear regression or do linear regression after this design or something like that. There's some other possibilities. But yeah, without knowing, let's put it this way, there's so many things that can go wrong with medical studies. I don't want the math to be what falls down. I don't want that part to let us down, so I want to know what works. And while I see things that can go wrong, I remain nervous. And I should say I've also seen some bad papers out there. So I have seen papers where people propose things using, some fancier machine learning methodology, which sounds nice, but then it only works if n is really big. And then when I try to do a back-of-the-envelope calculation to figure out how big n has to be, I've discovered we're never going to get there. So I'm also very cautious about trying to do things that work with small data. I mean, because fundamentally, you don't get big data in a lot of these things. If you're doing some sort of, again, public policy intervention or something, there are only so many experimental subjects you have, and actually it's unethical to be using more than you need.
Amazing. Last question.
Well, thank you for the great talk. I guess my question is, in terms of sort of some of the properties of this randomized procedure, because I'm thinking in the case where you have spillovers between these units, then you want to ensure positivity of the design in the sense that it should be possible for some of these units to not always be in the same group.
Yeah.
So in some sense, are there some guarantees of this procedure?
So there are a few things to think about. So there is a crude guarantee in one of the versions of the paper that says that you have some lower bound on the probability that two units are in the same group or different groups. So we can bound those away from 0 and 1, not as nicely as I would like. It, I believe, did not make it past the referees to the current version. So, by the way, I should just tell you, the paper is long. I mean, it's whatever Jazz allows plus 100-page appendix. If you look on arXiv, you will see sort of different appendices, somewhat written for different audiences. The first version was really written for computer scientists, so some of you may like that more. But yeah, we do have some bounds. But really, if the units are not independent in their response to treatment, you should really be doing something more than what we're doing here. My co-authors, Chris Harshaw and Frederick Savvy, have a few papers about that. So if you take a look at their work, you can find much more rigorous treatments of what to do if you can have contamination between subjects.
Well, let's thank Dan for this wonderful talk and for enlightening us and bringing mathematics and rigor to our thinking. Thank you, Dan. All right, Dan is available if some of you would like to come down and have a quick chat with him.